Okay, now I want to think about a scenario where we have a capacitor C1 and a capacitor C2. C1 is charged up with a quantity of charge Q. Okay, now if we think about what's the energy on C1, well, the energy is going to be equal to a half QV. When we connect these two together, the situation is going to change and the charge will spread itself around. Assuming these two capacitors are identical, and we'll go into the scenario what happens if they're not. You can do it working out yourself, but if assuming they're identical, that half the charge is going to leave and it's going to spread itself around evenly. Okay, so we just think about the situation for C1. If I just say energy of C1, in the initial case it's going to be half QV. In the second case, well, we can say it's going to be a half times by Q upon 2 times by the new voltage. But what will be the new voltage? Well, let's think this through. Because we know the capacitance is given by Q over V, well, this ain't changing. This capacitor is not going to change for anything at all. If we've got half the potential, sorry, half the charge, we're going to end up with half the potential difference. And so if this drops to half its value, the potential difference, V, is going to drop to half its value as well. And I think you can simply say that if we compare this scenario to this scenario, well, this is a half and a half again. Forget about the initial, this bit here, but this is half and this is half. So altogether, this is basically saying that from these two statements here, we can say that on C1, the energy is a quarter of the original. Now let's think about what's going on C2. Well, C2 had nothing in their energy on it at all before. That was originally had nothing. Now it's got the energy is of course a half. It's got half the charge, Q upon 2. And of course, as we said here, if the charge is Q, if Q upon 2 gives V upon 2 in this scenario, it's going to be the same in this scenario, if that makes sense. And so this is going to have V upon 2 as well. So this is going to have a quarter of the energy of the original on there, yeah? Of original, i.e., I can't spell original, but hey, doesn't matter. If a quarter of the original energy is on the C1 now and a quarter of the original energy on C2 now, well, we can say that basically half the energy is lost. Again. Now, worth mentioning at this point, this would only work, the mass of this would only be the same if these two are identical. The point is this: when you can connect two capacitors together, the potential difference across them is the same. Okay, and from that you can say, well, if V equals Q upon C, then you can say, well, I can work out that if I've got two capacitors in parallel, they've both got the same potential difference across them. I can do a bit of this, and I can say Q1 over C1 equals Q2 over C2, and you can basically work out the ratio of the charge because you know the ratio of the capacitances. Okay, and if you know the ratio of the charge, you can basically solve for it. It's pretty straightforward. Okay, so that's the first thing: energy in capacitors, and of course energy lost when you charge a capacitor from a cell, and energy lost when you charge a capacitor from another capacitor.